Okay, we are giving the permission. Okay, you can check now.
Right. Yeah, it's fine.
Okay, please share your slide.
Sure.
So in this talk, Soumya will be talking about properties and application of entanglement of indistinguishable particles.
Right. So thank you. So I have completed my PhD about 1 year ago, and I have joined as a research engineer in Tata Consultancy Services as a research and incubation. So I hope Anirban, who is our team, so you have shown the video of him. He's presenting in quantum chemistry yesterday, I think, or the last week, Friday. So in the industry meet, right? So now I will talk briefly about the research that we are doing in TCS Incubation Center. Then I will go to this topic. So this topic is my PhD work, right? So
I think your slide is not in full screen mode. Can you
right,
make it full screen?
Right, it is in full screen. I think. Is it okay now?
No, still not in full screen. So I think by pressing Control L or F5, you can make it full screen.
Is it okay?
Okay, go ahead, go ahead.
Okay, okay. So you can see the slides, right?
Yeah, we can.
Okay, okay, that's fine. So, so at TCS, we are working about 5 years, and we have a team of 50 quantum specialists, and with 7 PhD, we have published 20 papers and 6 patents, and we have customers all over the world. So we have partners with IBM, DOA, Ocean PyQ, AWS, QNew Lab, QCTRL, Microsoft Azure, Zapata. And our objective is experimentation on various quantum platform, benchmarking and maximizing performance. The algorithm for current NSQ hardware, resource estimation, and partner with these early adopters or POCs for quantum exploration. So our focus area are in quantum machine learning, that is image processing, time series forecasting, quantum optimization, capacity planning, workforce optimization, vehicle routing, and loading. In quantum simulation, some Monte Carlo simulation, chemistry simulation, molecular simulation, and material study. And I particularly work on quantum security, that is post-quantum cryptography, and quantum random number generation. So we have engagement on European automotive major customers, large pharma customer in US, some chemical manufacturer in India, and some telecom players for quantum communication. And this is all about quantum at TCS. And now I will be talking about this secure communication. So this quantum communication that we are doing in TCS. So you know that the market predicted value is in 2028 is about $5,269 million. And we see a year of about 20%. So you know that there are 2 types of quantum communication, that is QKD and post-quantum communication. So the security type on QKD is unconditional, this is and for PQC it is conventional, that is computational. QKD is secured against omnipotent eavesdropper, and PQC is secured against attacker by quantum algorithm. QKD impact is long-term and PQC is short-term, and in terms of robustness, QKD is independent of computational advancement, but PQC is retroactive for vulnerability exist. We know in QKD, so there are 2 approaches, that is continuous variable approaches, that is cost-effective and higher key rate. and it is compatible with current telecom industry. For discrete variable, it covers longer distance and it is stronger security proof. And we are working with some telecom sector for fiber-based QKD at 1550 nanometer. This is scalable over metropolitan networks. And global internet sector, that is fixed-based QKD at 18 nanometer. This is scalable over the global intercontinental areas. And there is some integrated photonic sector. You may heard of the news of this rough team who is working on Germany, right? So this chip-based QKD at 1550 nanometer. So this is the miniaturization, right? So we are working on QKD readiness, working with different companies like QIQT23, Unilabs, Quantum, SIGTech, Quintessence Labs, Viva, etc. for rapid quantum commercialization and product and the products. We already know that BT and Toshiba has launched some commercial trial at London, and China is already using QKD over 200-kilometer link, kilometer fiber link, and USA is using this deployment of dark fiber in QKD. We are also participating some of the standardization for CDOT. So last about in March, there was the standardization seminar at Delhi for CDOT. So they have published some QKD standardization and we are a part of it. And we are obviously another standardization body, that is ISO Workforce 14 and some TSDSI standardization. And you can see our TCS point of view document in quantum QKD, right? So, and we are open to some intern position and also full-time position. So any of you are interested to join TCS, you can directly email on my this email ID, right? So I will be providing the email ID. So now let's go to the topic. So this talk is based on two published papers at Physical Review Wave. One is hyper-rapid entanglement, indistinguishability, and two-particle entanglement swapping. And another one is the maximum violation of monogamy of entanglement for indistinguishable particle by the measures that are monogamous for distinguishable one. Right? This is the overview. I'm not going. Now, this is a very introduction slide that I tell in every talk. So this is a motivation for us who are doing this PhD or masters. So you know that Max Planck was the father of quantum mechanics, right? But when he was started his journey as a PhD student, then his advisor Philip John Pauli at 1874 told him that it was probably not a great idea to study theoretical physics since there was nothing much left. But thankfully, he did not listen to his advisor and continued his journey. So in 1900, he invented the black body radiation, and that is the birth of quantum theory, right? So we know that in 1935, EPR paper raises the question about completeness of quantum theory and suggested that a theory is possible which is both complete, that is local and deterministic. But in 1974, Bell proved that no local realistic theory can reproduce the prediction of quantum. So this is an introduction of the quantum information, and you know that this year the Nobel Prize is awarded for the verification of this Bell's theorem, right? Now, there are certain types of quantum correlation, right? So one set that is classical correlation and another set there is some different quantum correlation. So Bell non-locality, this is the strongest one, you can say. So this is like the strongest to weakest one. So there comes the steerability, then comes entanglement, then comes discord and the coherence. So we are mostly interested in this entanglement, that is the middle of, you can say, these 5 quantum correlations. Right. So in the world, there are 2 types of particles. That is, one is non-identical particle, another is identical particle. So non-identical particles are always distinguishable, right? You can distinguish two non-identical particles by their color, mass, etc. But identical particles, they can be made distinguishable, they can be made indistinguishable, right? So in the figure A, so see that there are two particles, two red particles, and they are completely identical. But they are so as they are quantum particles, so they have certain wave function associated with it. Let us assume that S1 is the position of the particle A, where say 99% of the wave function is associated, and S2 is the wave function of particle B. So based on S1 and S2, though these two particles are identical, you can assign two different values, that is A and B, since they are this wave function are non-overlap, right? So they're identical but distinguishable by their spatial location. Now, if the particles are made close enough, say in S3, then their wave function are completely overlapped. Then these two particles becomes identical but indistinguishable, because you cannot label these two particles. You cannot say in these two portion, which particle is A, which particle is B. Right. Now I will go through some of the known notion, that is quantum teleportation and hyper-rapid entangled state. So we know that quantum teleportation can be done in distinguishable particles, right? So that is proved in 1993 paper by Bennett. And in 2018, it was shown that quantum teleportation can also be done by indistinguishable particles, right? Similarly, EPS theory was proposed for distinguishable particle in 1935. This was shown to be again exist for indistinguishable particle in 2018. Entanglement swapping, again proposed in 1993, known to be exist only for distinguishable particle, but a paper in 2019, they have shown that it is also exist for indistinguishable particle. So we know that there are some quantum properties that exist earlier for a distinguishable particle. Now they can also exist for indistinguishable particle. Similarly, this duality of quantum entanglement, they were proposed for indistinguishable particle in 2013 by Bose and Divonkar. And they are again shown to be exist for distinguishable particle in 2006. Now, a general question arises that is there exist any quantum correlation or application that is unique to only distinguishable particle and only indistinguishable particle, right? So this is a question that intrigued me, and I do some investigation whether this exists or not, right? So you know that quantum teleportation is a process of transferring unknown state from one region to another. I think you already know about this quantum teleportation. I am not going through it, but I am going through the definition of quantum fidelity, that is the overlap between the initial and the final state, right? So initial state if it is X, final state if it is B. So how much similar X is to B, that is defined by quantum fidelity. If X is completely similar to B, then the fidelity is 1. We say that it's a unique fidelity. Now, we know that unit fidelity 1 with distinguishable particle proposed by Bennett et al. In 1993, and Low Franco et al. Have shown the fidelity for indistinguishable particle for quantum teleportation is 5/6. And Margellino et al. Have shown that it is possible to asymptotically achieve the unit fidelity, right? So they have shown if the number of quantum particles goes to infinity, the fidelity goes to 1. So there is an open question: is it possible to perform some unit fidelity quantum teleportation using indistinguishable particles? So this comes an another open question. Now, there exist some different types of quantum entanglement. Suppose A is a particle and B is another particle, and 1 and 2 are the degrees of freedom. If entanglement exists between the similar degrees of freedom, say A1, B1 and A2, B2, then we say that is hyperentangled state. If entanglement exists between different degrees of freedom, say A1, B2 and A2, B1, then we say it is hybrid entanglement, right? If both are exist, we say normally hyperhybrid entanglement. Now, this hyperhybrid entangled state was proposed by Lee et al. Using two indistinguishable bosons, right? So there is an open question that is hyperhybrid entanglement possible for two indistinguishable fermions? Right. So is a scheme for hyperhybrid entangled state proposed by Lee et al. Applicable for two indistinguishable particles? And this can indistinguishable particle exist hyperhybrid entangled state through some other scheme? So these are some open questions. Now, this is the circuit of Lee et al. For hyperhybrid entangled state. I am not going through it. And this is hybrid ring splitter used in hyperhybrid entangled state. So we are going to, due to this time limitation, we are going to the main theorem. We have shown if quantum particle, either distinguishable or indistinguishable, can simultaneously produce and perform hyperhybrid entangled state and unique fidelity quantum teleportation respectively, then using that, cloning of any arbitrary quantum state is possible. So using logical predicate logic, we can write that hyperhybrid entangled state and unique fidelity quantum teleportation, including we have this theorem. So this theorem, index is unknown particle if say x degree. We have this theorem, say phi x degrees of freedom, and phi pq is hyperhybrid, right? So if you can perform Bell state measurement with phi x and p1 and perform suitable unitary operation on q1 and q2. So you can say p1 and p2 are two different degrees of freedom of particle p, and q1 and q2 are two different degrees of freedom particle q, and they all are entangled. P1, Q1, Q1, Q2, P2, K1, and P2, Q. So if you perform Bell state measurement on phi x on P1, you can have using suitable unitary transformation this phi x to some phi q1 and phi q. So we have two copies of phi x in phi q1 and phi q. Thus, we have performed cloning using unit fidelity quantum teleportation and hyperhybrid, right? So, but we know in quantum there is a no cloning theory. So cloning is impossible in quantum. So we can write this as if cloning is not possible, then either hyperhybrid entangled state is not possible or unit fidelity quantum teleportation is not possible, right? So these two equations will satisfy. This is similar to the proof of the Bell's theorem that you can see, that either the world is local or the world is deterministic, right? So we know that unit fidelity quantum teleportation can also be done using distinguishable particle, right? So for distinguishable particle, then hyperhybrid entangled state must be impossible. If this is possible, then we can done clone. Similarly, hyperhybrid entangled state is possible for the distinguishable particle, indistinguishable particle, then unit fidelity quantum teleportation must be impossible for indistinguishable particle, right? So we have got answer that some quantum properties that suppose hyperhybrid entangled state, this is a unique property for indistinguishable particle, and unique fidelity quantum teleportation, this is a unique property for distinguishable particle. So earlier the picture was say entanglement swapping, steering, metrology, all was in quantum distinguishable plus indistinguishable. So we can done all these properties using distinguishable and indistinguishable. Now we got some other properties in this only distinguishable and only indistinguishable. For only distinguishable, we have unit fidelity quantum teleportation. and only indistinguishable we have hyperavid entanglement. So we can also try to fill up this set. So till now we have only one unique property, we can try to fill up more unique. So this is the broad contribution of us that we made these two extra sets. Earlier it was not only this set, our result has made these two extra, right? This is the broad picture of our work. Then, so in summary, we can say that no hyperavid entangled state for distinguishable and no unique fidelity quantum deliberation for indistinguishable. And we have also proved hyperavid entangled state in fermions. You can see in the paper. And we have proved some degree of freedom traceout rule for indistinguishable particle. I am not going through that. So you can say interestingly, so it was known that degree of freedom traceout rule only known for indistinguishable particle. We have made it for the indistinguishable one. This is the mathematical formulation. So you can, I'm not going through it. I am going through our next paper. That is the correlation of monogamy of entanglement for two indistinguishable particles, right? So we know that monogamy is a rule of marriage. So we know in the society that you can only marry to only one partner. So you cannot marry to two different partners. This type of rule happen in quantum theory also. If one particle is maximally entangled with another particle, we cannot have any entanglement with any other particle. Mathematically, you can write that the entanglement between A and B and entanglement between A and C is less than entanglement between A and B. Right? I think you all know this. Now, does monogamy always hold? No. So if you increase the dimension of the particle and if you change the entanglement measure, sometimes monogamy of entanglement is violated. So monogamy depends on the dimension of the particle and the entanglement. Right? So you can say using concurrence and Q monogamy of entanglement can be found. But in two dimension and concurrence entanglement measure, monogamy of entanglement is always right. Now we can define the monogamy violation in two ways. That is maximum violation of monogamy and non-maximum violation. If these two elements, say Emax is the maximum value of any entanglement, then E of AB and E of AB, AC less than Emax, but their sum is total Emax, then that is the non-maximum violation. Another way is violation, that is maximum violation. Both the entanglement E of AB and E of AC are equal to E. So we are focusing on this maximum violation, right? So we know this is no cloning theorem. So we know that if a particle maximally violates the monogamy, then again that will imply cloning, right? If A and B and A and C are maximally violated, then they can imply the cloning. So we can easily prove that. So we have proved that in qubit system, indistinguishability a necessary condition for the violation of monogamy entanglement. So we have shown that although in distinguishable particle, maximum violation of monogamy imply cloning, but for indistinguishable system, you can have a maximum violation of monogamy that will not imply cloning, right? So this is we have proved by using a sample state, right? And that so we have proved it theoretically, and this experimental implementation we are already collaborating with some institutes so that can implement this state. We have shown that using concurrence entanglement measure, using indistinguishable particle, this maximum violation of monogamy is possible. I'm not going through the mathematical details. You can go through in the paper. Now there are some obvious questions that you can ask. So till now we know that for distinguishable particle, no cloning theorem and monogamy are two similar entities. But for indistinguishable one, no cloning theorem is more fundamental. Monogamy of entanglement can be violated, right? Now we are trying to find this application of the maximum violation of monogamy, and is this violation possible for some other correlation like steering, coherence, and this. And we have applied this theorem in some application of entangled indistinguishable particle. We have shown that I am briefly stating the result since the time is already up. So for entanglement swapping, it was known that entanglement swapping can require 4 indistinguishable particles, and it can be done using 3 distinguishable particles also. So it is possible to reduce the number of particles in entanglement swapping for distinguishable and indistinguishable. We have shown an entanglement swapping protocol using only 2 indistinguishable particles without using Bell-State model. So we have reduced the number of particles from 4 to 3 to 2. So using 2 indistinguishable particles, we can perform this entanglement swapping, right? So this is given on the paper. The analysis is also given. So you can go through. So in conclusion, in this talk, we have shown that no hyperorbit entangled state for distinguishable particle and no unit fidelity quantum teleportation for indistinguishable. We have shown the DOF trace out rule for indistinguishable, maximum violation of monogamy for 2 indistinguishable particle, and 2 particle entanglement swapping for indistinguishable. Now, in future, you can obviously explore some more quantum properties and application that is unique to either distinguishable or indistinguishable. And is this maximum violation of monogamy can arise for other type of correlation that I have shown earlier, like steering, coherence, and discord, and some application of this monogamy of intent, right? So thank you all. Now, if you have any question, you can ask. Thank you.
Okay, thank you, Soumya. So, is there any question from participants? Okay.
I have one question.
Yes, Ranjit.
Thank you for your talk.
Yeah, thank you. Thank you.
In one of your slides, you talked about distinguishable and indistinguishable particles. So in case of bosons, what degree of freedom you use to distinguish photons?
Right. So we have used these special degrees of freedom, right? So as you know, this the first slide. So partially, so I can give you the answer that we have used the special degrees of freedom to distinguish this photon, as I have shown in the first slide. Right.
Okay.
So the details is given in the paper, so you can go through these papers that I have given reference, and if you have any question, you can already contact me. The mail ID is given, right?
Yes, I agree. But in quantum, you have quantum numbers, right? Energy,
right.
then polarization. You can use those ones to differentiate bosons.
Right. We
if they
can
have
do that.
Yeah, if they have same and the coordinates, you can replace one by, for example, one is sitting in, they can't sit because we have Heisenberg uncertainty relation. But so at point 1 and at point 2, we can interchange. But okay, but I will read then the paper which you are mentioning, and in case some queries, I will let you know.
Sure. Thank you.
Okay. Any other question? If not, so let us thank Soumya. So thank you very much.
Thank you.
Okay. So, features through logical qubits.